All right, so we're going to continue our discussion of alkenes here today. We started off the course by talking about alkanes, hydrocarbons with all single bonds, and then we introduced our new functional group, alkenes. So these have at least one of these carbon-carbon double bonds here. All right. We spent some last time characterizing these alkenes. Today we're going to spend time talking about reactions of alkenes. All right, so alkenes undergo what are called addition reactions. All right, so let's take a look at an example of an addition reaction. We're going to look at a Lewis structure, and then we'll kind of graduate to our bond line structures. We're going to start with a very simple alkene here. All right, and what we're going to do is we're going to react our alkene with this small molecule. I'm going to say A and B here. All right, we'll talk about specific molecules. We're going to leave it as like a variable here to start out with. And what we're going to see in these reactions is our carbon-carbon double bond is replaced with just a carbon-carbon single bond. All right. We still have those two hydrogens on each carbon, so I haven't lost any atoms here. The only thing I've done is now added to either side of this double bond. So on one side, I'm going to put atom A, and on the other side, I'm going to put atom B. Okay, so in these addition reactions, that carbon-carbon double bond, specifically that pi bond, is broken, and we have a new bond. New bonds formed on either side, on both sides of what used to be my original double bond. Okay, so we're going to see a few different specific addition reactions where we replace this AB with specific molecules here, but they're all going to have this same basic format, right? You're going to start out with your alkene, your carbon-carbon double bond. You're going to break one of those bonds, specifically that pi bond, right? So now we just have a carbon-carbon single bond, and we've added two new bonds to either side of what used to be my double bond. Okay. All right, so our first specific addition reaction is what's called a hydrogenation reaction. So this is an addition reaction. Again, they're all going to be addition reactions. But we're going to be using a specific reagent here, H2, hydrogen gas. All right, so based on analogy of what we just did above, let's take that same alkene I want everybody to take a second and draw me the product of what you would expect if I react this alkene with hydrogen gas. All right, so first of all, what new functional group did you create here? You turned your alkene into what? Into an alkane, into only having carbon single bonds. All right, so again, I'm going to replace my carbon-carbon double bond with that carbon-carbon single bond, right? That's going to be true for all of our addition reactions. I'll put those original 2 hydrogens on there. All right, and then I'm going to keep these ones sort of colored in red so we can see specifically where they're being added in this molecule. We have one being added to one side and the other being added to the other side. Boom, boom. All right, so we've broken. Chemical reactions are all about making and breaking bonds. So in this chemical reaction here, we break that carbon-carbon pi bond, and we form 2 new carbon-hydrogen sigma bonds. I guess we also break that hydrogen-hydrogen bond, huh? Cool, so this chemical equation is not quite finished here. I've left out one very important thing. This reaction won't actually take place if you just mix an alkene with hydrogen gas. You have to have a catalyst to help speed this reaction along. Otherwise, it's going to take 1,000,000 years. We don't got 1,000,000 years to wait, right? So catalysts are all about speeding up reactions so that we can actually do it on a reasonable time scale, i.e. a day in the lab, right? So we have to do this reaction with a catalyst. So that is what this is down here. PD is just one of our elements on the periodic table, palladium. All right, it is not actually involved in the chemical reaction in the sense that it's not incorporated into our product at all. All right, it is just a metal that you throw in there that helps speed the reaction up, okay? Generally speaking, the role of a catalyst is really, really hard to pin down. In this case, we do know from studies that the metal, it's just a hunk of metal. The hydrogen will actually bond to that hunk of metal, and then the alkene can come and sit on top of it. It kind of holds that hydrogen gas molecule in place. So that's fun fact, all right? That doesn't really pertain to how we draw our products or anything like that. And in general, we'll see catalysts in here sometimes, and we're like, man, we got no clue what that thing's doing. You know what happened? Somebody was in the lab one day, threw it in, it worked. They're like, great, write it down. Let's use this going forward, okay? Sometimes there's a little bit more art than science in the chemistry lab. When something works, you stick with it, all right? There are so many protocols where people are like, why does this step exist? It's like, look, because it frickin' works. Could you substitute it for something else? Probably, but guess what? This one works, it's not broken, don't fix it, all right? Anyways, the role of our catalyst is not really important, but what is important is when you write your chemical equation, you're always going to have that palladium catalyst in there.
So this kind of thing would probably be in liquid form? The metal would not be, but
No, you like take hydrogen gas and you spray it over this metal. Yeah, hydrogen's a gas. And the hydrogen actually sticks to the surface of that metal. Metals are weird, okay? We use a lot of these transition metals. Why palladium instead of copper? Who knows, all right? I will say that the other one that you will see that does work, and again, who knows why, Palladium tends to be the go-to because this one is much more expensive, but you could also use platinum. I think there's a third one, but I don't remember it off the top of my head. Cool, so this is all well and good and sort of written out with our Lewis structures here, but we've graduated to these bond line structures. All right, so let's just do a few examples using our bond line structures. Okay, again, I'm going to use my more condensed form. I'm not going to draw out the Lewis structure of hydrogen gas. I'm just going to write H2 and my palladium catalyst.
Shapes, does the double bond always go on the inside?
It doesn't. I think I always put it there, but if you saw it like that, that wouldn't really be wrong. I do think convention would be to draw it like that. Alright, so I'm going to do this one. Now that we're getting into reactions, there's one sort of double checked. We talked about this with our radical halogenation reactions, but counting carbons is definitely the one double check you should always do. I need to make sure I have 1, 2, 3, 4 carbons in my product here. You'll see me tapping away when I'm drawing my reactions, and I'm just counting my carbons to make sure I have the same number on both sides here. So I need to draw a product with 4 carbons. Again, I'm going to take that carbon-carbon double bond and replace it with a single bond. All right. And then I'll be good in color here. These were my carbons that originally had that double bond. So these will now have that new carbon-hydrogen double bond. Okay. All right, I've added a hydrogen to either side of what used to be my carbon-carbon double bond and replaced the double bond with a single bond, okay?
Theoretically, do we have to draw them in?
Cool, no, so I wanted to draw these hydrogens in to make a point that those are the new bonds that were formed in this reaction. But of course, in our bond line structures, hydrogens are allowed to be implied. So you could draw it like this, and it might be a good idea in your notes to emphasize that that's where those new bonds are. But no, absolutely, you could just draw regular old butane, and this is indeed the product of that reaction, right? Because our hydrogens on our carbons can be implied. So either one of these would be perfectly acceptable. It might be good to have in your notes with the hydrogens drawn in there, but once you get good, you want to be able to see that those hydrogens are just implied there. All right, so again, I'm going to draw my 6-membered ring. And I'm just going to replace that carbon-carbon double bond with a single bond. These used to be my double bonded carbons, so now each one is going to get that new hydrogen. Or again, you could have just drawn a hexagon and left your hydrogens implied. That's perfectly fine as well. Cool. All right, so a hydrogenation reaction, you can convince yourself, is necessarily where we turn an alkene into an alkane. Right? We're replacing that carbon-carbon double bond with just a carbon-carbon single bond. Okay? The next reaction we're going to study are what are called halogenation reactions.
So for the additional reactions, that was turning alkenes into alkanes?
Specifically for a hydrogenation reaction, where you're using H2 as your reagent. We're going to see a bunch of different addition reactions that use other things. They won't necessarily create alkanes, but when you use H2, you will necessarily turn an alkene into an alkane.
That's sort of like, the outcome that can happen?
Correct, yeah, there's no other thing you can do, because you're reducing that double bond to a single bond. Yeah, and we're going to see, so now we're going to talk about halogenation reactions. So again, these are addition reactions. They're all going to be addition reactions. But now we're going to add one of our halogens. Halogens are usually represented with this uppercase X. All right, but X can be any one, and we don't have a periodic table in here, can be any one of the halogens, those sitting in the second to last column on the periodic table. F, Cl, Er, or I.
Why are they usually represented as X?
Don't know. It's just what they picked.
It's kind of different.
So uppercase X2 is often a stand-in for a halogen. It's not even always the case. You'll see X as a variable to represent other elements, but for halogens, they do sort of default to this X2 representation. You will see that a lot.
Because they probably behave.
It's just a variable, right? So they pick a variable, right? You use T for time. You could use M, you could use anything, right? It's just a variable. We stick to one thing and you just kind of see it over and over again. There are a few halogens that work way better than the other ones. And so chlorine and bromine are the ones that you'll see the most. They just work much more effectively than the other halogens do. Okay, so again, let's first illustrate this with our Lewis structure. I'm going to use bromine as an example, but again, you could substitute in any halogen. And these ones will not have any sort of a catalyst. They work with just throw bromine in there, it'll react plenty fast. All right? So take a second and draw me the product that you would predict here.
Would it be wrong to put like BR2?
No, that's the exact same thing, just in a condensed form. So I'm specifically drawing out the Lewis structure of BR2 here. All right, same exact pattern that we've seen. We're going to see this throughout the day here. Our carbon-carbon double bond is replaced with a carbon-carbon single bond. We don't lose any of these hydrogens. What am I going to add on to each of these carbons? One of those bromines. All right, so you get one bromine on each carbon here. And I'm going to be good and put in my lone pairs because bromine likes to have one bond and 3 lone pairs.
Why couldn't you have gotten rid of like one of those hydrogens? Stay
You
in
can't, so a carbon-hydrogen bond is really hard to break. They're actually considerably strong bonds. If you remember when we did our radical halogenation reaction, that was a reaction that does break a carbon-hydrogen bond, but you need a free radical to do it, something incredibly unstable to do it. So generally speaking, unless you're going to put in a metric crap ton of energy, you're not going to break a carbon-hydrogen bond.
So it's easier to break the double bond.
Absolutely. That pi bond is particularly weak, and we talked about how it had, it's weak because of the geometry of that alkane, right? It doesn't sit between those 2 carbon atoms. It's really exposed on top and below. So it's just a pair of electrons that is much more accessible than the ones that are tucked away in the middle of the molecule. Yeah, and I mean, to be clear, we're saying when we replace a double bond with a single bond, it's really that pi bond in there that gets broken, right? That double bond is a pi bond and a sigma bond. Well, the sigma bond stays put. It's just that pi bond, that weird shaped bond that extends above and below that gets broken in this process. Okay, again, so this is written out all kindergarten chemistry-wise, but we've graduated to our bond line structures here. So let's again just rewrite this using these bond line structures. Use another halogen. Okay, so I'm going to draw in my 5 carbons. I have my carbons that were originally my carbon-carbon double bond. So now to each one, I'm going to add that halogen. All right, remember we don't want to like put our bond down here that looks ugly. We want to space these things out as much as possible, so my other chlorine will be pointed up. Don't forget your lone pairs when you're drawing your bond line structures, your halogens. When you write it in this condensed formula here, they don't bother putting in lone pairs. But when you do your bond line structures, you have to make sure everything's got a complete octet, that everything's got their lone pairs. All right, so same principle. This one's a little bit more funky shaped, but nonetheless, we're going to draw our carbons here. Get rid of this pi bond, that's what's going to be replaced. Okay, this one is now using bromine, so I'm going to put a bromine in. On either side. What's up?
So what I was thinking is, since there's no double bond and it's not locked in place, I like the bottom carbon, I kind of like tweaked it out so there's like...
Totally. Yeah, so I kind of kept my backbone structure the same. If I was drawing this from scratch, I would maybe put, whoops, that's not going to work. Put those two bonds spaced out a little bit better. And they could be pointed any way in space for exactly the reason that you're saying, right? That single bond can rotate freely. So my bromine could be pointed over here to the left. It could be pointed to the right. You just kind of want to space this out. I think it is a little bit easier to see your products, how they're formed, when you keep the basic shape of that molecule the same. When you start twisting stuff around, it can be a little bit harder to see how where you started led you to where you're going, all right? But nonetheless, and either one of those products would be correct. All right, these are the same thing.
What was the name of that? That would be
2, 3, 4. So 1, 2 dibromo 2-methylbutane. Of course, right? Yeah. All right. So the next one is going to be very similar, but this is what's called a hydrohalogenation reaction. All right. We're going to see that this is very, very similar to start out with, but we are going to have some added complications here that we'll throw in the mix. So first of all, this is when we do an addition reaction with a hydrohalogen. So again, my X in my formula here are one of my halogens. HF doesn't work too terribly well, but the other ones all work really well. What did I call that before? Oh, these are the ones that you'll see the most. If you remember from general chemistry, all of those, HCl, HBr, and HI, are all strong acids. HF is a weird one. It's not quite as strong. It'll work, but you'll have to wait a little bit longer. So again, let's just take our very simple alkene, ethene, to illustrate this. All right, so now I have my carbon-carbon single bond. All right, the main difference, and we're going to see this is where the complication arises, is you're not adding the exact same thing to either side of that double bond. On one side, you're going to stick your hydrogen from your hydrohalogen. And on the other side, you're going to put the halogen. Okay. Again, we don't need a catalyst for this. That strong acid works very well all by itself. Let's again put this sort of in our bond line structure format. Okay. And we're going to do an example with a symmetric alkene. As well as an example with an asymmetric alkene. Okay, now I'm making this distinction here because I'm going to tell you that you actually get two products when you use an asymmetric alkene. Take a minute and see if you can't figure out why we would get two distinct products with an asymmetric alkene. Take my symmetric alkene here to one side. I'm going to add the hydrogen. On the other side, my bromine. Okay, so this 2-bromobutane product is what we would get here. Again, you could have left off that hydrogen. You don't have to draw it explicitly on there. But since it is a new bond being created in this reaction, it might be helpful to have it drawn. Okay, so for this one, again, I'm going to draw my 7 carbons, right? 2, 4, 6, 7 carbons. Well, that's not that. I'm going to get rid of that carbon-carbon double bond. On one side, I'm going to add my hydrogen, and on the other side, I'm going to add my chlorine. But I said that there were 2 products of this reaction. This would be one of them. How would I get my second product? Put the chlorine on the other side, right? So let's make a distinction here between these 2 carbons. I'm going to color one in red and one in blue. Well, this would be my product if I added my chlorine to my red carbon, but I would get a different product if I added the chlorine to the blue carbon? All right, and you can convince yourselves that these are indeed different molecules because they got different names. The one is 2-chloroheptane, and the other one is 3-chloroheptane. All right. If we played that same game with a symmetric alkane, we swapped our bromine and our hydrogen, we'd have the exact same molecule, just drawn in a different way, right? So with a symmetric alkane, you don't have to worry about it. You're only going to get one product. But for an asymmetric alkane, you got to be careful. You may get two products.
You just typically draw both.
Just draw them both, all right? So I did throw this caveat in there, may get two products, all right? And that's because there's this other level of complication that we have for this reaction specifically that we haven't seen before, what's called regioselectivity. Okay, so this word regioselectivity, what the heck does that mean? This is this phenomenon we see when a new bond is specifically preferred in a particular location in your molecule, all right? So our new bond prefers a specific location. All right, so we're going to take an example to illustrate this. Let's take 1-pentene. Okay, we're going to react that with HI, and everybody's going to take a second and draw me the expected products of this reaction here. Okay, so based on analogy of what we just did, you would put your halogen on one carbon and the hydrogen on the other, and then you would swap. So now I'm going to draw my other product. H is here. And I is here. Okay. Again, I took this asymmetric alkane and said, all right, in one, I'm going to add the iodine to one carbon, and in my second product, I'm going to add it to the other. Cool? All right. It turns out that only one of these two products is actually formed in this reaction. This product right here will not be formed. So, like, what the heck? What gives? We just went through all this stuff, all right? There's a big difference between this example and the one that we did previously. And that is the fact that the classification of these two carbons is different. This one this one right here is a secondary carbon, and this one over here is only a primary carbon. And this particular reaction has what's called regioselectivity, where that halogen is going to prefer a specific location in this molecule. Does it want to be on the more or the less substituted carbon? Based on what I told you about what our product is. The more substituted carbon, all right? So the halogens will prefer to go on whatever the more substituted carbon is. Truthfully, you will get a mixture of both of these products, but it's like 95-5, right? A big preference for one location over the other. And what I'm always going to be asking you for is your major product, right? So in this case here, we're going to draw our major product. And again, the whole idea is this reaction has regioselectivity, where the halogen prefers the more substituted carbon.
That just with certain molecules?
So we'll stack some examples next to each other so we can see why when it matters and when it doesn't, all right? Okay, so when I looked at this alkene, I said, all right, one of those carbons is a secondary carbon, the other one's a primary carbon. That means that my halogen is going to prefer that more substituted carbon, right? So that was the product that I drew. Why did we not have that same consideration in our first example? Here we said that we're going to get a 50-50 mix of these two products. Why did I not just get one? Because they're both secondary carbons. They're both the same. You can't have preference for one or the other because they're both the same degree of substitution. So in this case, I will have two products, right? A 50-50 mix of these two products because the halogen won't prefer one over the other. Again, these are both secondary carbons. But in my next example, now I have a mismatch where one of them is more substituted than the other. So again, that halogen is going to prefer that more substituted carbon. All right, so we got a few different layers of complication here, right? We started out with these hydrogenation reactions, and everybody's like, oh man, this is going to be a piece of cake. Yeah, it is, because you're adding the same atom to both sides of that molecule. So there's no sort of difference if you swapped them, right? Now all of a sudden we're adding this HCl, this asymmetric molecule, to our double bond, and the way we attach it is going to matter, okay? Cool, so let's just practice this a little bit more. The reason why is actually well understood, but it's not something that we go over in this class because it involves what's called the reaction mechanism. So there's another layer of organic chemistry that you would study in the 2-semester course called mechanisms, where you show how electrons are moving, all right? So there is a reason why, but it's a little bit more complicated than what we're going to go into. But it has to do with the way that the electrons move when you do your reaction, where the bromine is going to prefer the more substituted carbon. So if you're interested, I can point you into an explanation, but I don't want to go over it here and confuse everybody, basically. Okay, so for this symmetric alkene, all right, I can fold it in half here and it's perfectly symmetric. How many products are we going to get? Just one, right? Doesn't matter which one of those carbons I pick, I would get the same product. I'll put the halogen on one and the hydrogen on the other. This one, I didn't do a good job coming up with examples because this is also a symmetric alkene. So how many products would we expect? Just the one, all right? Importantly also, these both have that same degree of substitution. They are both tertiary carbons, but they are both the same, right? So we don't have a preference for one over the other. If you drew this where you kept kind of your basic backbone structure the same and just kind of shoved the bromine in there, that's perfectly fine. If we were being good, we could space these methyl groups, this methyl group rather, and this bromine out a little bit more. Either one I'm fine with, all right? Cool, but now this one we have an asymmetric alkene. So are we going to get two products or are we still just going to get one product? We are only going to get one product here, all right? Why is that? Because of that regioselectivity business. I'm going to look on one side of my double bond and I'm going to say, what's the degree of substitution here? How many neighbors does that carbon have? 3. And I'm going to jump to my other bond and I'm going to say, how many neighbors does this carbon have? What's my degree of substitution?
2.
Only 2. So if they were both the same, then I would put a halogen on each of them, but we have a difference here. So we're going to have a preference for one side over the other. My iodine is specifically going to go on that more substituted red carbon. And then I guess to do the example that I kind of meant to do but messed it up, let's just do one more. There we go. All right, so now I have this asymmetric alkene. Am I going to get one or two products?
Two.
Now I'm going to get two. All right, so why is that? Again, it's asymmetric. If I look at this one and classify it, this one's a tertiary carbon. And if I jump to the other side and classify it, this one's also a tertiary carbon. So it can't prefer one side over the other, so you're going to get a 50-50 mix of both. So I'll have one product where I'm going to draw my halogen on that blue carbon. And then a second product, whoops, didn't work out. Where I draw my halogen on that red carbon. Not I. Cool. All right, so we have a little bit of a complication here with regard to these reactions are hydrohalogenation reactions. If you have a symmetric alkene, you don't really have to worry about these complications. All right, no matter what side you choose, you'll get the same product. If you have an asymmetric alkene, you got to watch out. You may have regioselectivity, where one carbon is more substituted than the other, so that's where the halogen is going to go. Or you have them match, so you're going to have two products. Rather, you have them with the same degree of substitution, so you're going to have a mixture of these two products, a 50-50 mix. Okay, so our last reaction of our alkenes are what are called hydration reactions. Again, just like all of our reactions of alkenes, these are addition reactions. But what do we think we're going to be adding to our alkene for hydration? Water, exactly. Okay, I'm going to draw my water molecule HOH because I'm trying to emphasize here that how you're going to attach this water molecule to your alkene is one carbon will get an H, the other carbon will get the oxygen, the OH. All right, so in this reaction, we're going to add a hydrogen to one side and an OH to the other side. We haven't talked much about this functional group other than to recognize it. What are these molecules with these OH groups in them? What do we call those? Yeah, it's a hydroxyl group, and the functional group category is alcohol. So So we can turn an alkene into an alcohol using these hydration reactions. All right. So I used this kind of simplistic way of drawing our water molecule to make a point. Our reagents for these reactions are quite a bit uglier than what we've seen before. All right. You use a kind of a complicated cocktail of catalysts and water in order to accomplish these reactions here. So hydration, reaction, reagents. All right, so let's start out with a simple symmetric alkene. We're going to have 3 different sets of reagents to accomplish these hydration reactions, and we'll talk about the similarities and the differences here in a second. All right, remember by reagents, I mean what's on my arrow here. Okay, these reagents are all going to accomplish the same hydration reaction. Hydrogen on one side and an OH on the other. I didn't leave myself enough room, that's okay. Okay, so our first one is the simplest, kind of the cheapest. That uses sulfuric acid and water, and then you heat it up. You heat the whole mixture. You throw, water in there with sulfuric acid, and you boil it up, and that's what catalyzes your reaction. Both the acid and the water would be considered catalysts there. You kind of just list them all together. This is what we would call acid catalyzed hydration. It's great, it's super cheap. There's really no cheaper reagent than sulfuric acid, right? Water we got on tap, we can use our burner, all right? So this is the great, cheap, effective way to do it. The problem is that you can't heat all your compounds up under these conditions. These are some pretty harsh conditions, and so not all molecules react under this. So when you can get away with it, you use your acid catalyzed hydration. But if you've just spent 100 years making only 2 milliliters of some special alkene, you're not going to throw it into boiling sulfuric acid. You're going to treat it with something a little bit more special, a little bit fancier. All right, and that's when you would use this set of reagents here. Mercury acetate. This combined with water will also catalyze this reaction. Okay, so this is what we call mercury acetate. Okay, you finish off this reaction by adding in what's called sodium borohydride. Okay, this is a really complicated list of reagents here. Importantly, your goal is not to understand what the heck mercury is doing in this reaction. Your goal is to site recognize this pair of reagents as producing an alcohol, as performing a hydration reaction, right? This isn't something you're going to be asked to have memorized. You're going to see, for example, a substrate and this reagent, and you're going to draw me what the product of this reaction is, right? So again, not about memorizing these reagents. We got some ugly lists. Why mercury acetate? I don't know, because it works, right? Why not platinum acid? I don't know. I didn't make the rules here, but it works great, right? So that's why they use it. Okay, and the last one is another kind of fancy one, and we're going to see that this has a particularly special use. This uses what's called borane, BH3, in tetrahydrofuran, a solvent, THF. All right, so these are 3 different reagents that will each catalyze a hydration reaction. The borane one is what's called hydroboronation. All right, we of course got some overly complicated chemistry sounding words going on in here. Okay, cool. So let's talk about the similarities and the differences here between why you would use one or the other. Really sort of boils down to, again, that regioselectivity. Okay, I used a symmetric alkene, so either one of those hydration reactions would give us the same product. But now let's do the same thing looking at an asymmetric alkene. And we're going to hit this asymmetric alkene with our 3 different hydration reagents. Sulfuric acid, water, and heat. Mercury acetate, water, and sodium borohydride. And then finally that fancy borane. Okay, so what we're going to see is these first 2 reactions, the acid catalyzed and the mercury acetate, are both going to put that OH group on that second carbon. So what would we say? These reactions prefer the more or the less substituted carbon? The more substituted carbon. So just like we did before, I went through and I said, all right, this one is a secondary carbon, and this one is a primary carbon. Well, in these 2 reactions, it's that more substituted carbon that is favored. So OH on the more substituted carbon. Right? For y'all's purposes, you can literally lump these 2 sets of reagents into the same category in your mind. They both do the exact same thing, all right? Obviously, I'm lying to you a little bit. I kind of gave you a little bit of a preview telling you that not all alkenes can survive under these conditions of being heated in concentrated sulfuric acid. But for the purposes of this course, we're not going to really dive too much into it beyond that, All right, so for our purposes, these two do the exact same thing. They are regiospecific in that they prefer the more substituted carbon. All right, the borane is going to be the weird one. This one is also regiospecific, but in the exact opposite way. Here, you're going to do the same process of looking at your degrees of substitution. A primary versus a secondary. But these BH3 hydration reactions, these hydroboronation reactions, they prefer the less substituted carbon. Oops. Okay, so we could either make what's called 2-propanol, where the OH group is on the second carbon, or we could make 1-propanol, where it's on the first carbon, depending on which hydration reagent we chose. Cool. So not only do we have these hydration reactions, we also have these different choices that we can make depending on what alcohol product that we're looking for. We have these two here, which again, we're just going to lump together in the same category in our mind. These are both going to prefer the more substituted carbon, all right? Or we have these, our hydroboronation reactions that prefer the less substituted carbons, okay? Cool, so we're gonna run out of time, but let me just show you one great kind of study tool that you can build that will help you out, and we call these reaction wheels. We just learned a bunch of reactions of alkenes, all starting with that exact same substrate, right? So a great way to summarize these is to start out with an alkene and then draw a little wheel where you say, all right, this is going to be my H2 and palladium. But then over here, I'm going to draw the product of if I reacted this with Cl2. And what about over here? Let's instead choose HCl. And then over here, we're going to do our acid catalyzed hydration. And over here, we'll do the product of our hydroboronation. Okay, and so you can sort of fill in this wheel here with all of these different reactions that we learned. Draw the product for the hydrogenation reaction here, your hydroboronation reaction. And then you got this little wheel that summarizes all of the reactions that we learned in this particular lecture, right? Our reactions of alkenes kind of all put together in one place so you can kind of see the similarities and differences, all right? These are great little study tools to build. You could then, when you're studying, switch out this alkene for another one and fill in that same wheel, right? It's just a good study tool of having these reactions all next to each other because it's kind of summarized what it is that you need to know. What's up?
On the right top one, isn't it supposed to be switched? The BH, like the number 2 and then the left one are together and then the other one separate, number 1 separate?
No, so it's borane in THF and then what's called hydrogen peroxide and sodium hydroxide. Cool.